Let's take a moment to summarize the key elements of the general framework we've developed for analyzing algorithms. These include defining the problem size, identifying the basic operation, considering different scenarios for time complexity, and finding time complexity for both iterative and recursive structures. By combining these components, we can build a structured, formal approach to mathematically analyze both non-recursive and recursive algorithms. We will start with the general plan for analyzing non-recursive algorithms. After that, we will apply a similar plan to recursive algorithms. The general plan for analyzing non-recursive algorithms begins with deciding the problem input size as a parameter to the time complexity, followed by identifying the basic operation that is located in its innermost loop. If the time complexity of the algorithm is denoted by Cn, where n is the problem size, the next step is to determine the different scenarios of Cn. I mean whether the analysis to find Cn is every case, or best, worst, and average cases. For non-recursive algorithms, usually they consist of loops, maybe a single loop or nested loops. And to analyze such algorithms to find the time complexity Cn, you need to count the number of iterations of these loops and how many times the basic operation is executed in each iteration. The result is a summation expressing the time complexity Cn. The framework's primary goal is to find the order of growth of the algorithm's running time as its input size goes to infinity. And in the last step of the general plan is to find the closest form of Cn, or establish its order of growth using the asymptotic notations big theta, big O, and big omega. To apply the general plan for non-recursive algorithms, we will be using examples to illustrate each step. Up to this point, most of the algorithms we've looked at were simple or toy examples. Their main purpose was to help you understand the core ideas behind the analysis framework. But now, to apply this framework more formally, we will turn our attention to real algorithms that solve practical problems. Our first example is a classical one, finding the maximum element in a given array of n elements. For a brief description of this algorithm, at line 2, the algorithm starts by assigning the first element of the array to a variable named max. This variable will keep a track of the maximum value found in the array. Starting from index 1 up to index n-1, the algorithm iterates through the rest of the array. In each iteration, each element at index I is compared with the current value of max, and if this element is greater than max, then max is updated with this new value. Once the loop finishes, the algorithm returns the value of max. Before we analyze the algorithm using the general framework plan, let's first do a detailed analysis. Although this step is not required, but doing that will help us identify the basic operation easily. As shown in the table, there is a single assignment at line 2. Then at line 3, we have a for loop. Its initialization or assignment happens once. The loop condition is checked n times, that is once for each iteration plus one final check that causes the loop to exit. And the increment operation is performed in -1 times, once at the end of each iteration. At line 4, we have a comparison operation that repeats in -1 times. Now, when analyzing the assignment operation at line 5, we need to consider different cases because its execution depends on the condition at line 4. In the best case, the assignment is never executed, that is 0 times, which occurs when the first element in the array is the largest. In this case, the condition is always false throughout the loop. On the other hand, for the worst case, the assignment executes in -1 times, once per iteration of the loop. This happens when the array is sorted in ascending order from smaller to largest, so the condition is always true. As for the return statement, it is executed exactly once at the end of the algorithm. Now let us analyze the algorithm using the general framework plan. As you recall, the first step is to determine the input size. Since the algorithm processes a list, the input size is simply the number of elements in the list, which is n. The next step is identifying the basic operation. Since the algorithm relies on comparing elements, specifically the comparison at line 4, and this happens in every iteration of the loop. Therefore, the key comparison at line 4 is our basic operation. Next, we need to specify the type of the analysis. Since the comparison is performed the same number of times, regardless of the specific input values, we consider this analysis an every case analysis. Finally, in the final step of the framework, to find how many times the comparison is executed, we sum over the loop from 1 to n-1, and the evaluation of the summation is n-1, which belongs to big theta of n. Our next example is the analysis of the unique element algorithm. The algorithm returns true if the given list to the algorithm has no duplicate elements. Otherwise, it returns true. I mean, it checks whether all the elements in a given array of n elements are distinct. The algorithm uses two nested loops to compare every pair of elements in the array. The outer loop passes over each element one by one, and the inner loop compares that element with every element that comes after it in the array. More specifically, for each element at index I as controlled by the outer loop, the inner loop begins comparing from the element at index I plus 1 and continues up to the last element in the array. That's why the outer loop stops at index n-2, ensuring that the last comparison is made between the elements at indices n-2 and n-1. If at any point the algorithm finds two elements that are equal, it immediately returns false because the array contains duplicates. If the algorithm completes all comparisons without finding any equal pair, it returns true, confirming that all elements are unique. Let's move on to the analysis of the algorithm. From observation, it is clear that the input size is n, representing the length of the array. And the basic operation is the key comparison performed at line 4. Since the algorithm stops execution as soon as it finds the first two duplicate elements, then the number of key comparisons is not the same for every instance of the algorithm. So number of comparisons of AI equal AJ not only depends on n, but also on specific input values. Let's see n be the number of comparisons. If the first two elements in the array are equal, then only one comparison is needed. This represents the best case scenario. On the other hand, if the array contains no duplicates, or the only duplicate is at the end, for example the last two elements, then the algorithm must perform all possible comparisons, which corresponds to the total number of iterations in the inner loop. This total can be calculated by summing over the two nested loops, resulting in a big theta n square complexity. Let me now walk you through the details of this result. To find the time complexity of the algorithm for the worst case, we build summations from the two nested for loops. So we write C for the worst case of n is equal to. Now for the first summation, it will be for the outer loop, I goes from 0 up to n-2. And for the second summation, it will be for the inner loop, j goes from I plus 1 up to n-1. Since the comparison is executed only once in every iteration of the inner loop, so the inner summation will be unity of a summation. The evaluation of these two nested summations is equal to summation I equals 0 up to n minus 2. Now for the inner summation, we have 1 inside the summation. To evaluate it, we take the last value minus the first value plus 1. So the last value is n minus 1 minus the first value, which is I plus 1 plus 1. Now minus 1 plus 1 is equal to 0. So this is equal to summation I goes from 0 up to n minus 2 of n minus 1 minus I. We will distribute the summation over this expression. And this is equal to summation I goes from 0 up to n minus 2, n minus 1, minus summation of I goes from 0 up to n minus 2 of I. Now in the first summation, n minus 1 does not depend on I, so we can take it outside the summation. And in the second summation, this is arithmetic sequence. So we can make it start from 1 instead of starting from 0, because adding 0 to the summation will not affect the final result. So this is equal to n minus 1, summation I goes from 0 up to n minus 2 of 1, minus summation I also goes from 0 up to n minus 2 of I. The evaluation for this summation is equal to n minus 1. So we have 1 inside the summation, so the evaluation will be the last value n minus 2 minus the first value, which is 0 plus 1. So this is equal to n minus 2 minus 0 plus 1, it will be n minus 1, minus the closed form formula for the general summation for the arithmetic sequence is n times n plus 1 over 2. Now for this summation, all what we do, we replace n by n minus 2. And the result is n minus 2, add 1, it will be n minus 1 divided by 2. To simplify this expression, we will take n minus 1 over 2 as common factor. And in the first term, what remains is 2 times n minus 1 minus n minus 2. And this is equal to n minus 1 over 2. Now, as you can see, we will have 2n minus 2 minus n plus 2. So minus 2 plus 2 is equal to 0. So this is equal to n minus 1 over 2. And we have 2n minus n, which is equal to n. This is equal to half n squared minus half n, which belongs to big theta of n squared. Now from this summation, we can do simple calculations that will avoid us to do all of these calculations. Let me show you. So if we want to compute the summation for I goes from 0 up to n minus 2 for n minus 1 minus I, we will evaluate this summation over the variable I. So when I is equal to 0, it will be n minus 1. When I is equal to 1, it will be n minus 2, and so on. So as you can see that the numbers are decreasing. So what will be the last value in the summation? We substitute for I with n minus 2. So n minus 1 minus n minus 2. This is n minus 1 minus n plus 2. N minus n is equal to 0, and 2 minus 1 is 1. So the last value is 1. So what will be the number that is before 1? Since these numbers are decreasing, so the number that is before 1 in the summation is 2. So here we can say that this is a plus 2 plus 1. Now we can build a new summation by taking the summation from right to left. So we are adding 1 plus 2 plus 3 until n minus 1. So this summation is equal to summation I goes from 1 up to n minus 1 of I. Using the general formula or the closed form formula for this arithmetic summation, it is equal to n minus 1, you add 1, it will be n over 2, and this is equal to half n squared minus half n, which belongs to big theta of n squared. The time complexity for the algorithm for the worst case is big theta of a quadratic function. The third example is a numerical algorithm that finds the product of two matrices A and B of size n by n and store the result into a third matrix C. In this example, given two n by n matrices A and B, we need to find the time efficiency of the definition-based algorithm for computing their product C. In general, each entry Cij in matrix C is computed by a summation that goes over row I of matrix A and column J of matrix B. The algorithm uses three nested loops to compute each entry of the matrix C. The outer loop goes over the rows of A, the middle loop goes over the columns of B, and the inner loop performs the multiplication and addition to compute each entry of the matrix C. For each entry Cij in the result matrix C, it is computed by taking the dot product of row I of matrix A and column J of matrix B, and this involves multiplying corresponding elements and summing them. Let me give you an example. In this example, we have two matrices A and B, both of them of size 4 by 4. Their product matrix is C, is also of size 4 by 4. So how the product matrix C is computed from the matrices A and B? In other words, how each entry in the matrix C, Cij, is computed from the entries of the matrix A and the entries of matrix B. To compute the value of the entry Cij, we take the sum of products between row I, that is in matrix A, and column J, that is in matrix B. For example, to compute C12, then we need to take sum of products between row 1 in matrix A, this is row 1, and column 2 in matrix B, and this is column 2. And we have this formula. So the value of C12, we take sum of products between 4 times 2 plus 1 times 5 plus 3 times 1 plus 2 times 4, which is equal to 24. To compute the sum of the products, the algorithm needs a summation variable. The entry itself is used as summation, where first it is initialized to 0, then it is used to sum the products in every iteration of the inner loop. To analyze the algorithm, we begin by noting that the input size is n, which represents the common dimension of the square matrices A, B, and C. The basic operation is the multiplication performed inside the innermost for loop. Since this multiplication at line 6 is executed the same number of times regardless of the specific values in matrices A and B, the analysis applies to every case. To determine how many times the multiplication is executed, we examine the structure of the three nested loops. The outer loop runs from 0 to n minus 1. The middle loop also runs from 0 to n minus 1. And the inner loop likewise runs from 0 to n minus 1. From these loops, we construct three nested summations. Each is from 0 to n minus 1. Since each summation is independent, I mean no summation depends on an index of a previous summation, then each is evaluated to n, and the total number of multiplications m of n is equal to n times n times n, which is equal to n cubed. And this gives us a time complexity of big theta of n cubed. The fourth example is an algorithm that finds the number of binary digits in the binary representation of a positive decimal integer n. The algorithm uses a counter to count the number of binary digits of the integer n. The counter is first initialized to 1, and repeatedly the value of n is divided by 2 until it reaches 1. For every division, the counter is incremented by 1, And after exiting the loop, the algorithm returns the value of the counter. Why division by 2 is used to count the number of binary digits of n? The reason is that when dividing n by 2, the number is shifted one bit to the right. Hence, every division corresponds to one binary digit of n. To find the time complexity of the algorithm, we first determine the input size, which is equal to n, followed by determining the basic operation, which is either the comparison n greater than 1 or any of the two statements inside the loop. They differ by exactly 1. But when tracing the algorithm for some samples of n, it is observed that the number of comparisons of the condition n greater than 1 is in fact equal to the value of count that is returned by the algorithm. In other words, finding the number of comparisons is the same as finding the number of binary digits of n. That's why it is better to consider the comparison n greater than 1 as the basic operation for the algorithm. Since the number of comparisons depends only on n and does not depend on specific values of n, then we have every case analysis. To determine the total number of comparisons, including the final one that causes the loop to terminate, we should track the values of n at each step. Since n is divided by 2 in every iteration, the comparisons happened for n, n over 2, n over 4, and so on, continuing until n becomes 1. So let I represents the value of n in each iteration. Then I equal to n divided by 2 raised to power 0 in the first iteration, n over 2 raised to power 1 in the second iteration, and so on. This continues until I equals to n divided by 2 to the power k, which is equal to 1. And this happened in the last iteration. Therefore, the number of comparisons can be expressed as a summation from 0 to k, resulting to k plus 1 comparisons in total. To express the number of comparisons Tn as a function of n, we need to find the value of k. To simplify the analysis and get the estimated answer, we will assume that n is a power of 2. I mean n is equal to 2 to the power of k, ensuring that the value remains an integer in each iteration, and the last value of n is equal to 1. Taking the base 2 logarithm of both sides gives k equals to log base 2 of n. Substituting this into the expression for Tn, we find that Tn is equal to log base 2 of n plus 1. If this is the estimated answer for the number of comparisons, then what is the exact answer? In fact, the exact number of comparisons is equal to floor of log base 2 of n plus 1. Let me show you how did we get this answer. To find the number of comparisons, we need to find the number of iterations plus 1 comparison for exiting the loop. So the number of comparisons equals to number of iterations plus 1. So let us find the number of iterations. So here we say number of iterations. Now by looking at the condition of the while loop, so the condition of the loop is n greater than 1, which is equivalent to n greater than or equal to 2. So whenever the value of n greater than 1 and the first value, that is integer, greater than 1 is 2. So we can change the condition, and instead of n greater than 1, we will make it n greater than or equal to 2. This will simplify for finding the answer as a floor of function. So in here we can say that and the last iteration, the condition is n over 2 to the power k, which is greater than or equal to 2. And as you can see that we are repeatedly dividing n by 2. The last value is n over 2 to the power of k. This is tested against the value of 2. By arranging the formula, so 2 multiplied by 2 to the power of k is less than or equal to n, and for the next value of k, it is less than 2 multiplied by 2 to the power of k plus 1. The left hand side, we have 2 to the power of k plus 1 less than or equal to n less than 2 to the power of k plus 2. Taking base 2 logarithm of all sides, then we have k plus 1 less than or equal to log of 2 of n less than k plus 2. And in fact, this is equal to k plus 1 plus 1. So here basically we say that the value of a floor log 2 of n is equal to k plus 1. So from the above expression, as you can see here, Tn is equal to k plus 1. So by substituting for the value of k, we say that Tn is equal to k plus 1, which is equal to the floor of log 2 of n because it is equal to k plus 1. And now for step 2, the number of comparisons is equal to the number of iterations, which is the floor of log 2 of n, plus one test or one comparison for exiting the loop. But notice that in this analysis, here Tn represents the number of iterations. But from our previous discussion, we use Tn to represent the number of comparisons. So in here, basically Tn is equal to the number of iterations, and we add 1 to it, it will give us the number of comparisons.